Hello, my name is Scott Grizzard from the University of South Florida. This is Calculus Lecture 2A. We're going to be talking about how to actually compute limits. So last time we talked about limits of sequences, and then on Friday in peer leading you talked about, you did this intuitive notion of the limit and how to graphically find it. So we're going to follow that up by talking this evening about computing limits to cops and a drunk. This is roughly sections 1.4 and 1.6 in the book. There's also some, we're going to do most of 1.4 and a little bit of 1.6, and then we're going to finish 1.4 next time. So where are we going to this? Why do we actually care about all of this, the limit stuff? So what we want to do is we want to move toward this definition for the derivative. Okay. And as you can see, it has a limit sign, and this is our old famous difference quotient here. And we can also think of it as a ratio of infinitesimals, which we're going to talk about in the future. But really what we're focused on here is getting to this definition. So we need this notion of limit, and we need to know how to compute these things in order to prove things about the derivative and compute the derivative. So that's where we're going with this. So in class this week, if you're in my class, you're going to be actually working through the limit laws. That's part of section 1.4. That's going to be in the worksheet. So that's where that will come in. And today what we're going to do is we're just going to talk about computing limits. We're going to talk about the guessing technique and how we can have sequences of X values, inducing sequences of Y values, which is kind of cool. And then some of the things where we can just sub in with direct substitution, and then tricks that we can do like factoring, multiplying by conjugates, that sort of things, just to help compute these things. And then we'll talk about limits of functions at infinity, and we'll revisit Nothing Else Matters, but now in a functional context instead of a instead of just a sequence context. And then we'll finish off by stating the one of the major theorems of section 1. Two cops and a drunk, sometimes known as the squeeze theorem, but that's boring. Two cops and a drunk is much more fun. So we're going to do that. Okay. And then after we do this, we are going to, next time, we're going to talk about how to write proofs and how to use theorems when writing proofs, which is one of the themes in this class that we're going to need later. Oops, don't know why that happened. Okay. So let's just start where we were. Remember that to have a limit as x goes to a, we need two things to be true. So the first thing that has to be true is that the function has to settle. So remember we had this example of not settling where we had sine of x just going meh, like this. Right? And sine of x does not settle. Right? It kind of oscillates between negative 1, between 1 and negative 1, and it never settles. Now, it does settle in the middle. So sine of x is perfectly fine if you want the limit as x goes to 0. But it doesn't work if you're going over to infinity. Another thing that must happen is that the limit from the left must equal the limit from the right. So here's a good example. Here, as we can see, we've got this nice little function here, f. And as we come from the left, it approaches 1. And as we come from the right, it approaches 1. So this is nice. It settles. It's not filled in right there, but that's okay. The limit from the left equals the limit from the right. And we have a limit that is nicely defined, so, and exists. So we have the limit as x goes to 3 of f of x equals 1. Now we can break these things. So here's an example, okay, of a function that doesn't settle as you go to 0. So settling as you go to infinity, that's kind of easy. But look at this one. Sine of 1 over x, which, which you would expect if you think about, you see, it's not defined at 0. But what happens here, this thing gets getting faster and faster and faster and faster as we go up. as sign gets as x gets closer and closer to 0, this thing oscillates faster and faster and faster. And we can see that behavior here. It just goes nuts when you get close to 0. If I put it on the other screen, we can actually zoom in here. So here's the view that we have right now, and as you can see, it's just going nuts as you get closer and closer to 0. And if I zoom in here, right, no matter how far I zoom in, this isn't helping, right? Zooming in doesn't help. It's still going faster and faster and faster and faster and faster. It doesn't matter how much I zoom in. It's still just not helping. Okay, it's going to keep oscillating and oscillating and oscillating, and there's nothing I can do about it. So this doesn't have a limit as we go to 0 because it just doesn't settle. It's just like, right now, it just looks like one big blob of red. And that's because, you see, look at all that. It's not settling. It just keeps going on and on and on and on and on. So that's one way that you can have a limit that fails. Another way is if the limits don't equal each other from the left and the right, right? So here I've got one where the limit as I approach 2 from the left is 1, and the limit as I approach 2 from the right is 1.5. Therefore, the limit doesn't exist. Here, the two left-handed limits, the left and the right, don't exist, right? So the limit here, the situation's even worse. Here, the limit as x goes to 0 from the right of sine 1 over x does not exist. And the limit as x goes to 0 from the left of sine of 1 over x does not exist. So here, everything's going bad, right? Here, the limits just don't exist, left and the right. Here, I've got left and right limits, but they just aren't equal to each other. And that can happen toward infinity, too. So here's our example, f of x equals 1 over x. It's the one that we're going to, again, I told you last time, please, if you don't understand this function, print it out, stick it on your ceiling right before you, so that every night right before you go to bed, you're looking up at this beautiful function. Okay, it's an important one. As I go from the left, I go up to positive infinity as I approach 0. As I go from to the right, as I come from the left, I go to negative infinity. As I go from the right, I go to positive infinity, goes 0. Its other limits are important too. If I go off to the right to infinity, I get 0. If I go off to the left to infinity, I get 0. But as I said, the limit from the right as I approach 0 is infinity. The limit from the left as I approach 0 is negative infinity. Therefore, the limit as you approach 0 does not exist. One popular way of guessing what a limit is to do what's called the sample method. So what I'm going to do here, let's look again at this reciprocal function. All right, what I'm going to do is I'm going to take a couple sample points, and I'm interested in what happens as x goes to infinity. So I want to guess what's going to happen as x goes to infinity of 1 over x by taking numbers that are bigger and bigger and bigger. So here I'm going to choose like 1, I get 1, 2, if I choose 2 as my x, I get 0.5, 10, I get 0.1, 100, I get 0.01, and so on and so on and so forth. So I'm guessing that as x gets bigger and bigger, y is going to go to 0. And I can sort of formalize this a little bit more. What I'm going to do is I'm going to take a sequence of x values, okay? In this case, my sequence is going to be n to the 10th. So these are the sample points I'm going to use. So I'm going to use, when n is 0, xn is 1, right? 0 to the 10th. And then y, which is f of 1, is 1. When my next one is going to be 10, that's going to give me a y of 0.1. My next one's 100, and that's going to give me 0.01. 1,000 gives me 0.001, and so on and so on and so forth. So what I'm doing is I'm taking sample points in x and getting a sequence. So I'm taking a sequence in x, and I'm getting a sequence in y by simply taking the f of whatever that next sequence value was in x. So let's look at this. I have a sequence of y values. So if f is a function, x is going to xn being a sequence of numbers in the x space. Xn, the sequence xn is going to, it's called induce a sequence in the y space by simply doing f of xn in the y space. So again, this was our idea. I got 0, I get 1, when n equals 0, I have 1, and then 1 over xn equals 1. So this would be 1 over x naught. Here I've got 1 over x1. Here I've got 1 over x2. Here I've got 1 over, that's a 2. Here I've got 1 over x3, and so on and so forth. This right here is 1 over x to the x7, not x to the 7th, x7. Okay, it's the 7th x value. All right. And so my hypothesis is that this thing goes to 0. So that's this idea of an induced sequence. Let's do another example. Here is one that I'm going to let f of x equal x squared, and I'm going to let my xn's get closer and closer to 0. So I'm interested in the limit as x goes to 0 of x squared. So what I'm going to do is I'm going to let x, my x values, be 1 over n. This should be an n, not an x. Okay, so x1 is going to be 1, x2 is a half, x3 is a third, x4 is a fourth, x5 is a fifth, and so on and so forth. So here's x1 in my x space. The corresponding number in my y space is right there. Let me label these. There's x1. And that is y1. Here is x2 at 1/2. And this right here is y2 at 1/4. And so on and so forth. There's x3. And so as I go this way in x, y is being driven down this way. Should write a plus right here because x is actually going to 0 from the positive direction here. Yeah. So as xn goes to a, yn is heading to L. This 0 here and 0 here. Okay. So that's how the sample point method works.
We'd like to get a sample of your brain tissue.
Okay.
We can also see this method work on the graph. So let's look at the graph of this thing. Right here I've set up, this is the function x squared. Now here I've set up my sample points. In x values, they are 1 over n. So if I wanted to label my x's, they'd be here, 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 here. You can't see them because I'm in the way. Here, here. So x is heading this way. Now y is going to go this way. And as you can see, as I zoom in here, we can actually see that my sample points are going to wind up getting closer and closer to 0. So as the x gets closer and closer to 0 from the right, the y's are getting closer and closer to 0. And I can do this, and then I can do another sequence. So let's say I want to do the sequence. Let's say I wanted to go from the other direction. I'm going to do the same thing, except I'm going to square it. So this is Tn, right? This is my sequence in the x. And this right here is my sequence in the y. And as you can see, as I come from the left, I get the exact same thing, right? It's going, as my x's are getting closer and closer to 0, so are my y values. Okay? Now, I want to be very, very wary of the sample point because it can give you in trouble. It's great for guessing, but it can lead you to astray. And here's an example of that. So let's say I want to take the limit as x goes to infinity of sine of pi x.
I think that would be extraordinarily dangerous.
Okay. Well, I've got a couple choices here for sample points. But notice what happens if I use integers. Okay, if my sample points are integers, look at what happens here. I'm going to wind up, if I've got an even integer, I'm going to wind up here. If I've got an odd integer, I'm going to wind up here. Either way, my northiness is 0. So when I start plugging in even that, integer values here, I'm always going to wind up with 0. So I pick 1, 2, 10, 100, 10,000. I'm always going to wind up with 0. Now, I can also always wind up with 1. Let's say I add n or 2n plus 0.5, right? So I start with 0, I get 0.5, then I get 2.5. I'll just throw some more even numbers in here, 1,000.5. I'm always going to wind up with 1. So if we look at what's happening in here, right here is the one where I've always chosen, I chose the integer values of pi, right? There's my, sine of pi. So this is n. This is sine pi of un. And I'm going to wind up with 0, 0, 0, 0, 0, 0, 0. And as I go off to infinity, I'm winding up with a sequence of zeros. And if you remember from the last time, a sequence of zeros, its limit is 0. However, if I plug in here, if I plug in this formula for my x's, 2n plus 1/2, I wind up with the northiness. I'm always at the top of the circle, and my northiness is always 1. So this sequence here is just 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and it looks like its limit is 1. We can do another example here. Let's go back to our old our formula for sine of 1 over x. Right? If we look at sine of 1 over x, our old sine of 1 over x here, if I take the sequence of x values to be 1 over pi n, then do sine of that Sn, right? So this is going to wind up being sine of pi n, right? Because when I take this 1 over pi n, it's going to wind up flipping. And I'm going to wind up with that same situation I was in again. As I approach 0, I'm going to wind up with, I go 0.1, I wind up 0.98, whatever. I wind up with 0. And as I get closer and closer to 0 in the x space, it looks like I'm getting closer and closer to 0 in the y space. But this right here, this sequence also has a limit of 0. And if I choose it, I'm going to wind up with that exact same situation I just had here. So here, this right here, this 2n plus 1/2, I put it in here. Oops, not that one. I put it in here, this 1 over tn, and it flips it again, and I wind up with a sequence of 1s. So as my n goes to infinity, my xn's go to 0, but my yn's stay at 1. And I get 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and it looks like the limit is 1. That does lead us to something interesting, though. Okay? If I have two sequences, so that both sequences are going to the same place in the x space, they both go to A in the x space, but they go to different places in the y space. The f of Rn and f of Sn go to two different numbers in the y space. This should be Ln. L1 does not equal L2. Then this limit as x goes to A does not exist. So now I have a criteria to say whether or not a limit exists. A testing criteria, if you want. If I can find two sequences going to the same place in the x space where their y sequences go to different points in the y space, I don't have a limit. Okay. So again, with our example, these were two sequences, right? Here was the evens. Here was the even integers. And here, right here, were all these numbers that always went to 1. Okay. I don't have something that settles as I went to infinity. So now we have a definition. We have a formal definition for the limit. It's different than the formal definition in your book, but it is a formal definition for a limit. If f is a function where a is in or near the x space, by the way, this near example, let's say that d is the interval 0, 1. Okay, then a could be 0.5 or a could be 1. A does not have to be in D, but it has to be adjacent in a sense. Okay, so that's an example of what we mean by in or near. So if I've got a in or near the x space and L in or near the y space, the limit of as x goes to a of f of x equals L if for every sequence x, so that Sn goes to a, f of Sn goes to L. So that is a perfectly good definition of the limit. Now, it has some problems when I want to prove something. Okay, it's easy to prove that a function, using this definition, it's easy to prove that something doesn't have a limit. But, it's hard to prove that something has a limit because every sequence, well, there's an infinite number of these sequences, and you're going to be here for a while. So, I'd like to get lunch at some point, but no, I'm sitting here checking all the possible sequences. You could never do it. You could wait till the end of the universe. You still haven't checked them all. But it does give us an idea of a formal definition. Now, there is a formal definition in your textbook. It's called the epsilon delta definition. So what you're going to do is let x be in or near the x space. A is something in or near the x space, and L is in, come here, there we go. L is in or near the y space, and f is some function. Let the limit as x goes to a of f of x equals L if for every epsilon greater than 0, there exists a delta greater than 0, so that if the distance from x to a is less than delta, then the distance from f of x to L is less than epsilon. So this is reminiscent of the definition that we had for the sequence. It's just got more pieces because now we've got delta running around, and now we still got the epsilon, but now we've got a delta running around. And if you're interested in the subject, I do have posted an extra video on this. It's important to note that the extra video is not required for this class. If you're a math major, you should be interested. If you're physics majors, you should also be interested, because you're going to need it when you start doing, when you want to do complex things, which of course you want because you want to study black holes and, do all those and gravitational lensing. But if you're not interested in those sorts of things, it's, if you're a chemistry major, this isn't very interesting. Again, if you're a math major, this is. So you can look at the extra for that. So let's look at some computational tricks for these things, right? We want to know how to compute them. Well, the easiest is direct substitution. So let's stick in a and see what happens. So for example, if I want to take the limit as x goes to 6 of 6 plus 5 of x plus 5, if it's a function that is very well behaved, and I'll tell you what those mean in a minute, I can just throw in 6. Now, be wary that you can wind up with something bad here. Okay, so for instance, if I take this function, f of x where f of x equals 6 if x equals 2, and x squared otherwise. if I take the limit as x goes to 2 and I just plug it in here, this right here is wrong.
Ray, this looks extraordinarily bad.
Oh no.
What?
That's bad. Okay? The limit here is not 6. The limit here, the limit of this function is going to equal the limit as x goes to 2 of x squared. Because notice that this is just sticking out there. Notice how this 6 is just sticking out there. Right? Here's most of the function looks like a parabola. 2 is going to be a little bit higher than that. Most of the function looks like a parabola, but then there's this space here, right, at 2. There, my axis is here. And this right here is the number 4. Here's x equals 2. Now, and here's x equals 6. Not drawn to scale. Now, if I have here, if I try to throw in the number 2 into this function, I'm going to wind up with 6. But it's not that. What it is that I really want the x squared portion for the limit. So I can't just toss in 2 into this bit. I have to notice that what's going on here is this kind of jump. Okay?
All right, that's bad. Okay. All right, important safety tip. Thanks, Egon.
So there are functions that direct substitution does work for. These are polynomials. Okay? So anything of the nature x plus 5, x squared plus 5, x squared plus x plus 5, x to the 15th plus x squared plus 2. All of these things are polynomials. You can direct substitute in on polynomials. You can also direct substitute in on rational functions where the number is in the domain of the function. Okay, so for example, if I've got x squared plus 1 over x minus 1, right, this is a rational function, and the bottom doesn't have a bad spot at x equals 0. The bottom has a bad spot at x equals 1, but not at x equals 0. So I can directly substitute in on this rational function, and I get 0 squared plus 1 over 0 minus 1, which is 1 over negative 1 equals negative 1. And the way I say I'm going direct substitution is writing ds on the top. Now, again, it only works for certain classes of functions, and we're going to get into where it works a little bit later in the course, in 2 lectures, actually. But for now, it works for rational functions and it works for polynomials. It also works for trig functions, where A is in the domain. And it works for algebraic combinations of these functions. So if I have 2 polynomials added together, it works for that. If I have 2 polynomials multiplied, it works for that. If I have a trig function times a polynomial, it still works. All right, as long as the A is in the domain. All right. Now, another way to do this is to factor if you get 0 over 0. So this is another trick. So here's x squared minus 4 over x minus 2 as the x goes to 2. So notice here I'm going to get 4 minus 4 equals 0 on the top and 2 minus 2 equals 0 on the bottom. So what I'm going to do is I'm going to factor the top. Now look how the two things square. The two x minus 2's cancel, right? This is the difference of squares. Okay, if you don't remember how to do that, come see me. You don't need the sum of cubes and difference of cubes formulas for this class, but you do need that difference of squares. You need to be able to recognize that. So I factor this and those cancel. And then I get the limit as x goes to 2 of x plus 2. This right here, x plus 2 is a polynomial. So this is a rational function, but 2's the bad spot. So I had to factor. I directly substitute in there. I get 2 plus 2 equals 4. Another thing to do is you can multiply by the conjugate. Okay. So what I can do is let's look at x minus 2 over the square root of x minus the square root of 2. Now, there's a little note to play here, and that is that you can actually factor x minus 2 into the square root of x minus the square root of 2 plus the square root of x, times the square root of x plus the square root of 2. It is a difference of squares, but that's not generalizable here. What we want to do, so there is a way to do this another way. But what we're going to do is we're going to multiply by the conjugate. And the trick here is to leave the thing that you're not conjugating out alone. Let me show you what I mean. So I've got this x minus 2 over the square root of x minus the square root of 2. I'm going to multiply by the radical conjugate here. And I'm going to wind up with the square root of x plus the square root. I'm going to multiply by the square root of x plus the square root of 2 over the square root of x plus the square root of 2. That's 1. Okay. Now, when I multiply that through, the bottom here is going to become x minus 2. And those are going to cancel. And I'm left with the radical of x plus the radical of 2. I directly substitute in on that. This is, it's not on my list, but radical functions. Oh, I did. Radical functions, when A is the domain, you can direct substitute on. So I substitute in on this radical function that's a sum of two radicals. And I get the square root of 2 plus the square root of 2. That's 2 root 2. Okay. So that's how you multiply by the conjugate. Now there's everybody's favorite. So special tricks for limits going toward infinity. This only works if A is infinity or A is negative infinity. If x is going to infinity or x is going to negative infinity, we have nothing else matters again. So if I've got two polynomials, by the way, this is what a polynomial is. I'll define it again in just a minute. So here are two polynomials, p over q. I take the biggest, nothing else matters, says I take the biggest, the coefficients and the x to the n, where the n is the biggest thing on the top and the m is the biggest thing on the bottom. Okay? And I say nothing else matters, and then I wind up with Cn over Am. Those were the two biggest things. But notice this only works if I'm going to infinity or going to negative infinity. Okay? It only works at those. It doesn't work for any finite a. Nothing else matters, only works for infinity things. So here's an example. The limit as x goes to positive infinity of 10x cubed plus 5x squared plus 3 over 200 minus x4 equals, nothing else matters. The limit as x goes to infinity, I pick the things with the highest coefficient. Here they are x cubed, 10x cubed, and on the bottom it's negative x4, x to the fourth. So I wind up with 10x cubed over negative x to the fourth.
'Cause nothing else matters.
A lot of those x's cancel, and I wind up with the limit as x goes to infinity of 10 over negative x, and that is negative infinity. No, that is not negative infinity. That is 0. Little mistake there. Right, this is negative 10 over x, and I'm going to infinity, so that's going to be 0. Okay, here's another example. The limit as x goes to infinity of x squared plus 10 over 5x squared. I'm going to just pick up the largest term. And I wind up with the limit as x goes to infinity of x squared, the 10 goes away, over 5x squared, which equals the limit as x goes to infinity of 1/5. This thing is 1/5, 1/5, 1/5, 1/5, 1/5, 1/5. Its limit is 1/5. Okay. Which gets into the question, here's the definition of a polynomial. Let P be a function. P is a polynomial if for every x in the x space, I can express P of x as an x to the n plus an minus 1 x to the n minus 1 plus blah, 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 plus a2x squared plus a1x to the first plus a0 x to the 0 being 1, so it's just an a0. Okay, here are some examples. X squared, polynomial. X to the 5th plus 2x plus 1, polynomial. Okay, h of x equals 1, polynomial. It's because all that's here is the a0. All of these other coefficients that you could think of would all be 0, and all I'm left with is this little 1 hanging out. That's a polynomial. Here's alpha of x is x plus 1 times x minus 1. That's a polynomial because I can multiply these things together, and I get x squared minus 1, which is a polynomial. Okay? So that's the formal definition of a polynomial. And we're going to see that again. So it's actually a kind of key definition for a lot of the things we're going to play with. And polynomials are nice. We like polynomials. Taking derivatives of polynomials is very nice. So what we're actually going to do a lot in physics and chemistry and all these things is we're going to estimate functions using polynomials. Because if we can estimate it using a polynomial, derivatives are easy to take. They're easy to compute. Computers like polynomials. They're nice. All right, so let's look at our big theorem for this section. We got a big theorem. We had nothing else matters. That's a small theorem. This is a big theorem. This is 2 cops and a drunk. We can ask you this theorem on the test, and you have to state it verbatim. Here is what it is. The idea, the big idea, and we're going to go over this in the quiz review, and then we're going to go over it again in the next lecture, in lecture 2B. Because in lecture 2B, we're going to look at how we prove things using this beautiful theorem. So here's what it is. Okay. Let f, top, and bot. Top and bot, by the way, stand for top function and bottom function. Be functions. A something near or in the x space. L something in or near the y space. So here's the setup. I've got this function that's always on top and this function that's always below or on bottom. Okay. And I've got an L here in the y space and an A in the x space. Now, what's going to happen is that for all x near A, the bottom function is below f, which is below the top function. The top function's on top, f is in the middle, the bottom function's on the bottom. Now, the other thing that's happening is that the bottom is as the bottom heads to A, as x goes to A, the bottom goes to L, and in the y space, and as x goes to A in the x space, top of x goes to L in the y space. So what I've got is these 2 functions that are heading to the same place. Okay, so the limit as x goes to A. Let's get rid of those things. The limit as x goes to A of bottom equals the limit as x goes to A top equals L. If those 2 conditions are true, then the limit as x goes to A of f of x also goes to L. So if I've got a function that's trapped between 2 other functions, both of which are heading to L as x goes to A, that means that f must be heading to L. It's trapped between them. And we'll talk about this some more in class when we go to the quiz review. But this I want you to have memorized before that, quiz 2B. Okay? And then next time what we're going to do is we're going to see how we can use this. We're going to go back through this theorem, really get some meat on it. And then we're going to use it to write proofs. And we're going to prove things that are very, very cool. Okay? So that's it for today. We had this idea that we talked about, this idea that I can have things that don't have limits even at finite points. Okay, I have things that don't settle or things with jumps or things where the limit from the left didn't equal the limit from the right. I went over this idea of taking sample points and why there was this big warning on the sample point method where it could fail. Then I talked about some computational tricks. So direct substitution, if you have polynomials, rational functions, radicals, trig, and algebraic combinations thereof. And then I talked about the fact that you can factor these things or you can multiply by the conjugate. Okay. And then we talked about nothing else matters, function addition. And then we defined 2 cops and a drunks. We stated the theorem. And again, this is preamble here up top. This is the stuff that's the meat. The if-then structure, by the way, is very important. When you do this on the quiz, I don't want these 3 bullet points alone. You have to have if this, then this. That if-then structure is very important. And then next time we'll do 2 cops and writing proofs. Okay, that's it for today. Thank you.
Ray, when someone asks you if you're a god, you say yes!